welcome developers. Welcome to your new favorite Devel YouTube channel, where we speak about the evolution of the blockchain space and we have practical tips on how to build on the blockchain with insightful knowledge tips on the particular protocols that are exciting to build on these days. In today's episode, or edition as the case might be, we shall be dissecting zkEVMs. zkEVMs stand for Zero Knowledge Ethereum Virtual Machines, and they are genuinely one of the most pivotal pillars that have existed over the last 6 months when it comes to conversations about blockchain scalability and transformation in our space, right? And I think, again, of course, over the next 6 months, we shall continuously be having these conversations about how Zero Knowledge Proofs and zkEVM go on to make our space as beautiful as possible. So it makes sense that we start off with this in this new series, right? So join me on this exploration. This is going to be a theoretical part. There's going to be a theoretical part to this series, and then it's going to be a practical part. So for this theoretical part, join me as I give you a small breakdown on the foundational topics in this space. Let's go. Firstly, let us recap 2 core concepts. First one is rollups, and second one is zero knowledge proofs. Rollups are layer 2 solutions that execute transactions off-chain but host compressed data on-chain. They oftentimes use things like either fraud proofs like optimistic rollups, or they use validated proofs like zero knowledge rollups to ensure correctness. On the other hand, however, zero knowledge proofs, or ZKPs, are probabilistic cryptographic protocols that are going to convince a verifier of a statement true without revealing any information beyond its validity. In blockchain, we usually use either zk stacks or we use zk snacks. Zk stacks stand for zero knowledge scalable transparent arguments of knowledge, while zk snacks stand for zero knowledge sourcing non-interactive arguments of knowledge. A zkEVM is an EVM equivalent virtual machine that goes on to generate zero knowledge proofs of state transitions. Predominantly has 7 different components, and the 7 of them are: number 1, a state manager that handles the Merkle partition tree for account storage; number 2, an EVM executor that processes the EVM bytecode, managing the stack, the memory, and storage; and number 3, the witness generator that creates witness for every operation executed; number 4, the circuit composer that translates the EVM operations to arithmetic circuits; number 5, the proof generator that uses the circuit to create zk snacks or zk stacks; number 6, the batch generator that combines multiple transactions into one single batch proof; and number 7, the on-chain verifier, a smart contract that verifies the batch proofs. The most challenging aspect here genuinely has been found to be the circuit composer, and because it must represent complex EVM transactions and operations like SS store and create2, and represent them as systems of arithmetic constraints, and oftentimes this requires sophisticated decomposition techniques. So zkEVMs predominantly use one of 2 different proof systems. The first one is Plonk, which stands for permutations over Lagrange basis for economical non-interactive arguments of knowledge, and this is predominantly skewed towards the snack side of things. And Fry-based snacks, the FRI stands for Fast Read Solomon Interactive Oracle Proofs of Proximity, and this is skewed towards the stacks. Fry-based stacks offer post-quantum security but larger proof sizes. Proof generation time is a critical performance metric in this world right now, and current implementations currently require at least several minutes to be done with the transaction, with the complex transaction. There have been several techniques that have been used to try to assuage this problem, and one of them, or rather 3 of them, I'm going to mention right now are: number 1, recursive proofs, which involves proving the correctness of other proofs; number 2 is GPU acceleration, which is just parallelizing my apologies, parallelizing proof generation; and number 3 is ASIC development, which is just custom hardware for zk snack computation. Now let's get a little bit technical. We are going to examine 3 different ways that zkEVMs have been implemented across 3 different protocols, and for these ones we're going to use Tycho, we're going to use Polygon zkEVM, and we're going to use Crow. Tycho uses a type 1 zkEVM aiming for full EVM equivalence. It implements a decentralized proving network using a bonded proving model and employs a unique pessimistic roll-up design, allowing for instant L to finality. Polygon zkEVM, on the other hand, implements and utilizes a custom zkEVM based on Plonk, which I spoke about earlier. It implements a state differential based approach for efficient proof generation, and then uses a zk roll-up bridge for asset transfers with a 7-day withdrawal period. I'm really proud of the work that has been done at these two places. And now for School zkEVM. School zkEVM, on the other hand, however, implements EIP 4844 for blob data storage and for reducing core data costs. It also utilizes a modular zkEVM design with separate circuit for CPU, memory, and for usage. So I think the last distinctive thing I know that they do very well is to employ a recursive snack for proof aggregation, which we spoke about earlier too. So I know this is only the second time that we are having this YouTube series, but you will notice a pattern in me looking at for the technical challenges that many of the solutions that have been presented have. So I'm going to follow the same pattern here too. There's some technical challenges that we are facing right now in zk development, and some of them are like, I have like 4 of them in my head already, 4 or 5 of them. So let's see. I'm thinking to myself circuit complexity, I'm thinking to myself precompiled contracts and what that means. But let me talk about circuit complexity first. Even operations like maybe AXT code copy or delegate call are notoriously difficult to represent efficiently in circuit form. Precompiled contracts are also a problem because implementing cryptographic precompiled contract in zk circuits is notoriously and computationally expensive. Non-determinism is also a problem I see because like handling operations like block dash highly depend on the L1 state. It's also the trade-off that happens between proof time and and circuit size trade-off, because more optimized circuits oftentimes lead to longer proving times, and it creates a quandary where we want to ensure that we have as much optimization as possible, but it also leads to longer proving times. I guess yet another thing I can think about off the top of my head is Ethereum upgrades. Implementing new EIPs, of course, have some implementation, will have some effect upon the zkEVM architecture. So those are some things I've thought about that may actually be key challenges in zkEVM development. zkEVMs represent an almost natural convergence of advanced cryptography, distributed systems, and blockchain technology. As developers, understanding the integrated architecture and challenges is almost as fundamental as anything else to building the next generation of scalable and private DApps. Whether you're optimizing for zk circuits, or you are designing L2 tokenomics, or you are building cross-chain DApps, or cross-chain bridges, or whatever it is you're building, a deep understanding of zkEVMs and what it can do for you is almost invaluable. So listen, I'm just genuinely excited. If only one person picks up from this video, an excitement for what zkEVMs are and what the zero knowledge technology underneath is about, I'm shocked. So put in the comments below what you're excited about and what you'd like me to talk about next after this. Thank you for staying with this deep dive. Like and subscribe for more advanced blockchain developer content and more DevRel, theory and all that exciting stuff. See you in the next video.